For this example, we're being asked to integrate e to the x times the square root of 1 minus e to the 2x. And so as with most integrals, what you have to do first is decide, what integration technique is this guy going to be? Is it going to be integration by parts? Is it going to be u substitution? Is it an inverse trig integral? Is it, this, that, or the other? And you go through your basic integration rules. It would be totally understandable if a student thought this might be u substitution because of the composition that we have. But unfortunately, I don't think that would work out, because if your u was 1 minus e to the 2x, then we would realize that our du would be negative 2e to the 2x. We can fix the negative 2, but this is e to the x, not e to the 2x. And so that doesn't work. Integration by parts doesn't work. You can try whatever you like, but I think the only thing that will fit here is this new integration technique that we've been studying called trigonometric substitution. Now, what made me think of this was the presence of this radical here. Having the square root in the problem made me think, oh, this could be trig substitution. It handles things that have radicals, specifically of the form a squared minus u squared, which is what this guy is. All right, and so if we think that it might be trig substitution, then here's what I want us to typically do. First thing we'll do is we will draw ourselves a right triangle, and then we will put the radical on one of the sides. And so it'll either be on one of the legs or it'll be on the hypotenuse. Now, because this is a minus, I think it would work better on one of the legs, because that way when we use the Pythagorean theorem, so if we write 1 minus e to the 2x, when we do the Pythagorean theorem, when we square this side and the radical goes away, we can add this term here, and it hopefully will cancel with this minus term that we have here. So that's why we put it on the leg. If it was a plus, we would put the radical on the hypotenuse. So we'll keep that in mind as well. Okay, so now what should go here and here on the other leg and on the other hypotenuse? Well, hopefully it's pretty clear. This would be e to the x, and this side here would be 1. Now, if you're not sure how to fill out a right triangle, I would recommend to go back and watch the theory videos. There's three-part video on trig substitution, and we talk about how to fill out a right triangle for trig substitution problems in those videos. But anyway, here's our right triangle that we're going to use, and this will let us do a particular substitution. We'll call this theta. And so I want to write e to the x and the radical expression both in terms of theta as opposed to e and what have you. So the relationship we want for e to the x would be sine. So sine of theta would equal e to the x over 1. So sine of x would be e to the x. And then the radical expression right here being the adjacent side, I think we'll use the adjacent and the hypotenuse, since the hypotenuse is 1. That would be a cosine relationship. Cosine of theta would be the square root of 1 minus e to the 2x. Okay, so instead of having these guys in your integral, you can replace them with these guys. And it turns out if you do that, the integral is a little bit easier to do. Now, so I've got e to the x, that's sine x. I've got the radical expression, that's cosine. I don't have dx yet, so just while I'm at it, let me go ahead and find dx as well. If e to the x equals sine of theta, then let me differentiate both sides. If I differentiated the left-hand side, then we would get e to the x times, we can go ahead and write out the full expression dx d theta, and this will be equal to derivative of the right-hand side, which would be cosine of theta. And then we would have e to the x dx would be equal to cosine of theta d theta. Okay, so we can substitute all of these different things in the e terms in terms of thetas and trig functions. All right, so let's do a little bit of rewriting here. All right, so we'll take this integral, I'll underline it in orange. All right, so I'm going to write it down here. This would become what? The integral of, let's do the radical term first. The radical term would be cosine of theta, right? Cosine of theta. And then don't be too hasty. You might look at this and say, oh, well, e to the x is sine theta. But then you would not have anything for the dx. But notice the equivalency that we have for dx is e to the x dx. E to the x dx. So together as a packet, it would equal cosine of theta d theta, right? So this is the integral that we have to compute instead of the original one. And this one looks much easier to compute. All right, so this would give us the integral of cosine theta times cosine theta would be cosine squared theta d theta. This is an even power of a trig function, so we know how to handle these. There's a nice trig identity that will reduce the power from being squared to not being squared anymore. It's 1 plus cosine of 2 theta, all divided by 2 d theta. This was just a trig identity that we know from our pre-calculus class. We have not integrated. I just rewrote cosine squared. So this goes to show you it's very important to know your trig identities. Because if you didn't know this trig identity, you would have a very difficult time trying to integrate this guy. All right, I see there's a 1/2 we can pull out. We'd have 1 plus cosine 2 theta d theta. All right, integrate this expression here. We'd get 1/2 times the quantity. Integral of 1 is theta. Integral of cosine 2 theta. There's some algebra that I'm not going to write out. This would be a little mini u substitution problem in and of itself. But at the end of the day, you would get 1/2 sine of 2 theta plus c. Okay, and you can check my algebra on that. All right, now it's time to start changing everything back in terms of our original variable. The original expression wasn't given in terms of theta, it was given in terms of x. But luckily for us, I've got some equivalencies where expressions that have theta are equivalent to terms that have x in them. So that'll be very helpful for us. So let me rewrite some of this here. So let's distribute this 1/2 right here to both of these terms. We would have 1/2 times theta plus 1/4, that's a half times a half, 1/4 sine of 2 theta. Now notice, let me stop for a moment. I don't have any equalities that have sine 2 theta. All I have is sine theta and cosine theta. But luckily for us, we know a trig identity. There's a trig identity that says, I'll jot it down here, sine of 2 theta is equal to 2 sine theta cosine theta. So that'll be helpful right here, sine theta cosine theta. Now why would I like to know such a thing? Well, these guys are not in terms of 2 theta, they're just in terms of only just a theta. So we'll write times 2 sine theta times cosine theta plus c. All right, and so for our final answer, I'm going to go back and write what these guys are equal to. So we'll have 1/2. All right, now what is theta? What is theta? Let's come back here. Well, theta, sine of theta was equal to e to the x. So would it be fair to say that theta would be equal to the arc sine of e to the x? I think it would be. And then we'd have a fourth times a half is, I'm sorry, a fourth times 2 rather would be a half. Sine theta is by definition e to the x, and cosine theta by definition is the radical expression. So we have e to the x times the square root of 1 minus e to the 2x plus c. Right? And this is our final answer. Now, what is that guy? What does this mean exactly? Well, this extremely difficult example that we started with, this difficult integral that we were given originally, we had no technique for how to solve this guy. But it turns out that if you temporarily substitute in its place certain trig functions based off of this right triangle, it turns it into an equivalent integral that has trig terms that we can integrate. And so that's the idea with all these trig substitution problems. You change it to trig functions correctly using the right triangle, you integrate it, and then when you get your answer, you put your answer back in terms of x. And so I'll bet you that if you take this guy's derivative, you take his derivative, I bet it comes back to this integrand right here. So it's pretty interesting that we were able to do that. So hopefully that helps you understand trig substitution integrals just a little bit better.